Okay, so the last class we looked at heat conduction in higher dimensions. So if you remember, we defined first our domain, we defined the boundary. Remember that the boundary is always defined as the closure of the set. That basically means the domain plus the boundary minus the open set, which is the domain. And we said, well, now we're going to divide this boundary in three different regions, where we are applying Dirichlet boundary conditions, one where we're applying the Robin type of boundary condition, and one where we're applying Newman boundary condition. And of course, those three cannot be overlapping. So this is the way you say that the intersection of all these different sets have to be equal to the empty set. And well, we express a strong form of a problem for which we need a given set of quantities. We started with the heat, the conductivity tensor. And remember, this is the way we express the mathematical notation for a tensor. So we have the domain is the closed set, and the codomain is basically RD cross RD. And then we have all the quantities. So this is the heat source, then the prescribed Dirichlet boundary condition, or heat in this case, the prescribed flux, and finally some coefficient that is going to be used, or film coefficient that is going to be used in the definition of the Robin boundary condition. And so the strong form is again find the temperature U such that the heat conduction equation holds inside the domain or in the open set, such that, and therefore we need boundary conditions, and the three boundary conditions that we are using are prescribed temperature equal to U bar on gamma U, and then prescribed heat flux, and then finally the prescribed heat flux has to be equal to this film coefficient multiplied by these two quantities, where U is the value of the temperature that you don't know, and U infinity is the value of the ambient temperature. Okay, so this is a strong form. And as we did over and over again, this should be something that you guys already know. Well, the weak form is derived by taking our differential equation, multiplied by some weight, and integrating over the domain. And we're saying by doing that this whole quantity is equal to 0. So in a sense, we are projecting that differential equation into a space. That space we call V. So this has to be valid for all W's in that space. That, if you remember, we are still in an infinite dimensional space. So as you can see, I'm repeating over and over these things because it's basically the same, right? And then you become used to it. So what we do in higher dimensions is some sort of integration by parts. So there is this identity that we used, and then by replacing that entity into the equation, what you see is that again the boundary conditions arise naturally, the natural boundary conditions. And so this last term here, we use the divergence theorem to replace basically the divergence of this quantity inside the entire domain, so in the open set, to an integral that is valid only along the boundary. So this is called the divergence theorem. And we use that, and we notice that this integral is, of course, in the entire boundary. But the entire boundary is composed by the boundary where you are prescribing Dirichlet, Newman, and Robin boundary conditions, right? And so this is essentially what I'm writing here. And remember that we got rid of the one where we're prescribing Dirichlet boundary conditions because the weight functions that we choose have this nice property that they are 0. They are exactly 0 along Dirichlet boundaries, and therefore we can get rid of that term in the formulation, and we don't need to deal with reactive fluxes in this sense, okay, in this case. And so the final abstract form of the weak or variational formulation is find U belonging to some space, right, such that the bilinear form equals to the linear form for all W's in that space. And then, well, for deriving the finite element equations, what we do again is now we're not looking anymore at an infinite dimensional space. We take a finite dimensional space, and in this context, we're looking at a finite element dimensional space, right? And so once we do the projection with these functions that we're taking from the same space, in which case we have, again, the Bubnov-Galerkin approximation, then we obtain something that in abstract form looks pretty much the same as the weak form, only that we have replaced U by UH and W by WH, and that's it. And the process is, again, the same over and over, and that is what we're going to look at today when we look at the elasticity in higher dimensions. Okay, so let's get started. So today we're going to look at elastostatics in higher dimensions. And if you notice, I started with elastostatics in 1D, and then I moved to heat conduction in 1D, and then I moved to heat conduction in higher dimensions, right? And now I'm moving to elastostatics in higher dimensions. And the reason I do that is obviously because the heat conduction in higher dimensions is still a scalar problem, right? So the temperature field, right, is a scalar field regardless of whether you're talking about 1D or 2D or 3D. Now in elastostatics, things are different. So in 1D, you have 1 degree of freedom per node, so it's a scalar field. But in 2D and in 3D, you have a vector valued field. So things are different, okay? But we start the same way, so we are going to define our, let's define our mechanics potato again, right? And again, there is going to be a part of the boundary where we are going to assign our Robin boundary condition, and therefore, let's denote that we have some sort of spring there. Remember that the Robin boundary condition is a mixed boundary condition. Then you have a prescribed traction on gamma t, right? Let's draw some arrows here. And remember also, and I think we discussed this in a previous class, if you don't have anything prescribed along a boundary, you're actually prescribing a zero traction. Okay, so it's the parts of the boundary where there is nothing going on. It's actually part of a Newman boundary condition where there is zero traction. Okay, this is my domain omega, and well, it turns out that again, this entire domain has a, normal field that we call n. So the normal at any point in the boundary is a field because it's changing the direction, right? It has a unit magnitude. And then there is also a part of the boundary. Let's do this. And I'm gonna do it differently here. So this is going to be gamma u, which is a part of the boundary with prescribed Dirichlet boundary condition. Okay, and again, we need some quantities. Well, of course, we start with a body force that now is a vector valued function that goes from domain omega to Rd. D is the dimensionality of the problem, so this is our body force, right? We need a prescribed displacement field that goes from gamma u to, again, Rd, so it's our prescribed displacement. Then you have the prescribed traction from gamma t to Rd. And then we are going to call this H, we're going to call it our elastic support tensor in this. And actually, this notation is slightly wrong because normally you define domain and codomain using columns, right? This is the way we use the definition of functions. And then again, this is going to be a tensor. And let's call it elastic support tensor. Yeah, so given these quantities, then the strong form is simply the divergence of the stress tensor plus the body force is going to be equal to 0, right? And notice that I'm using now vector notation, so this is no longer one equation. This is going to be 2 equations in 2D or 3 equations in 3D, and this has to be valid in omega. I forgot to say here that again we have the same notation as we had before for the definition of the boundary. So partial omega is equal or equivalent to gamma. That is the boundary. Again, we define that as omega minus omega over bar minus omega, and then the screen. Yeah, I know why that happens. It's because there is a. Okay, now it should not turn off. It is recording, yes. Yeah, and then this boundary is again can be. It's not overlapping, so gamma u, gamma t, gamma h is equal to the empty set. Those are standard definitions. You see them all the time when you're reading papers because this is a mathematically correct way to define this. Now, what are our boundary conditions? We cannot still solve this, and I'm going to talk a little bit about sigma in a minute because we have not defined what sigma is, but of course you know, all of you should know what this is, right? Because you have seen this in previous classes. So u has to be equal to u bar on gamma u, and then we use Cauchy's relation to relate the stress tensor to the attractions along the boundary on gamma t, and then we use the same to define our Newman boundary condition, that is basically u bar minus uh, and these are all vector quantities on gamma h. So that's it. This is basically the definition of our strong boundary value problem. Yeah? Yeah, okay. How about now? Yeah, disappeared. Good. So what are these things? Remember that we use this notation to denote that this quantity is our divergence operator, right? Sigma is the stress tensor. Yeah, and well, the stress is basically defined on omega over line, and of course it's a tensor, so it goes from omega over line or the closed set to RD cross RD. Yeah. And then what we're going to do, because we still need one equation to be able to solve this problem, right? We have the continuity equation that relates basically the strains to displacements, and we're going to stay in the small deformation theory regime that basically says that the linearized strain tensor is basically defined as 1/2 of grad u plus grad u transpose. And we're going to do this just to keep things simple. Okay? So now that we have the strong form, well, how do we get the weak form? And as you all know by now, we take this equation, we weighted that equation with a weight function, and in this case, we have basically a vector valued field, and therefore we need to weight this with a vector, and therefore we have W now is a vector, so we take the dot product between these two. Yeah, and then we integrate that over our entire domain, and then we said that is going to be equal to 0. And notice that I'm using here in the definition of the strong form, I'm using a 0 vector because I have 3 equations. But the moment I do this dot product operation, this is basically a scalar, and therefore my right-hand side is a scalar. Yeah, and this has to be equal to, of course, all vector valued functions W that belong to some space that again we're going to just call simply V naught. And the naught right there basically says already that those functions that you choose are going to be equal to 0 along the Dirichlet boundaries, so that we don't have to deal with reactive abstractions in this case, okay? Now, remember, it's a vector-valued field, and therefore W is a two-dimensional vector in 2D or a three-dimensional vector in 3D. That basically means that each component of W, the components of that vector, are going to be equal to 0 along Dirichlet boundary. Yeah? Dirichlet boundaries. So, how do we express that in mathematics? Well, we said that V naught is the set of functions, and I call them here V because, well, we can use pretty much any symbol to denote, but V is a generic term, right? So that V of X is a vector, and that is the way we express that, for all X in omega, such that Vi, and now I'm talking about the ith component of that vector, right, is belonging to the first order Sobolev space, right? And who can remember what that means? What is a Sobolev space?
And if you do the integral of the square functions plus the square derivatives, it's going to be 0?
No. The Sobolev space, if you remember, was the space of functions that were square integrable and which had derivatives up to a certain order that were also square integrable. So in this particular case, H1 is a set of functions that belong, that are square integrable. So each component of that vector has to be square integrable. Remember what square integral meant, right? That when you do the integral of that function in the domain, the result of that is going to be finite, less than infinity, okay? And then we take the derivatives of those functions and we do the same integral, and those are still finite, right? The integrals of those quantities are still finite. That is the definition of the Sobolev space.
Sobolev is more than one derivative?
Sobolev is more than, no, well, it depends on the order here. So I'm using H1, so that is basically the first derivative. But if you are using H2, right, that means that the first derivative has to be square integrable and the second derivative has to be square integrable. So those are, for instance, used in the beams problem, right? You have a fourth order differential equation, and then to balance derivatives, you end up with a second order derivative, and therefore you need those functions to be chosen from H2. Again, why do we do this? Well, because we don't want to deal with functions whose integral end up in having an infinite result, because we are relating the space that we're using to the energy space, and having an energy space that has, so a solution that has infinite energy, it is not in our interest for these problems, okay? Okay, so let's continue. Who remembers what we do next? Now we have to balance derivatives. And it is not very straightforward to realize what's going on here, right? Because I just look at the differential equation here and I say, well, it's the stress. But if you look at this, I'm applying the divergence of the stress. So there is a first derivative, and then the stress is linked to strain, which, by the way, I completely forgot about it. But the stress here, we're going to use Hooke's law. So stress is basically linked to strain using a fourth order tensor, right? So this is Hooke's law. And therefore, what you can see here is that strain has also the derivative. So I'm basically applying the gradient. The grad U is basically the gradient of the displacement field, and the gradient of a vector field is a tensor. And then when I take the divergence of that tensor, I get a vector. Okay? So you can see that there is a second order derivative there, and therefore we want to balance the derivatives, right? We want to have a first derivative on the displacement and a first derivative on the weight function, okay? Okay, so how do we do that? Well, we're going to use this identity, again, on identities. The identity is essentially that W dotted with the divergence of sigma plus grad W contracted with sigma, and we're going to talk about what that means in a second, is equal to the divergence of the transpose of the stress tensor operating on W. This is the identity that we're going to use. Now, I'm not going to tell you this time to just trust me, so I'm going to show you the proof real quick, so I'm going to write this down. You can do this also on your own to prove this is true, but we're going to start with this quantity right here, and we're going to take the divergence of that, and we're going to see how we're going to get these two terms, okay? So, if we take the first term like this, right, you can actually write this in component form as sigma ij. So we're using the transpose of that tensor. So it's sigma ij, ej, tensor, ei, and this multiplying. So this is being applied to a tensor. Remember that a tensor applied on a it's applying on a vector, right? So a tensor applied on a vector is also the result is a vector, right? So this is being applied on this vector that we're going to write wk ek, right? No, because it's transposed. Yeah. So when we do this, well, you can see that here I'm going to group all the scalar terms on one side. So it's sigma ij wk, and then this operation ej tensor ai applied on ek is basically the Kronecker delta ik and then ej. So this is something that you should have already studied from previous courses, and therefore this guy here, Kronecker delta, has basically the property of contracting one of the indices, and then I get sigma ij wi ej. So that is our first operation, right? But now we want to apply, of course, we want to do the divergence of that operation. So the divergence of sigma transpose operating on W, and by definition, let's write down what is the definition. Again, we have done this last class. By the definition of the divergence of a vector, the divergence of a vector is a scalar. So I take the jth component and I apply the derivative with respect to xj, right? So in this case, the jth component of that is just this quantity that you see here, right? So it's the derivative with respect to xj of sigma ij wj, and then if you apply basically the derivative of a product, then you get the derivative xj of sigma ij multiplied by wj plus sigma ij multiplied by the derivative of j with respect to xj. Okay? Sorry? Yes, you are so right. I am supposed to be using I here. So this quantity is supposed to be I. Thank you so much. Yeah, thank you. And so when you do this and you look at this term right here, right, this term is essentially the divergence of the stress tensor dotted with W. So it's basically the dot product between these two vectors. So the first vector is obtained as applying the divergence to a tensor, which is a vector, and then I dotted that with W plus, and this is an interesting term. So basically what this is saying is that I have to keep in mind here I have the repeated index notation, right? So every component here, sigma ij, is going to be multiplied by every component of something, right? The derivative of wi xj is grad w, right? So this is called the contraction between two tensors. Yeah? Well, so we're going to define that as an operation. Let me move this away. And then you may have seen also this in previous lectures, but if you have the contraction between two tensors, this is an operation that basically implies this. So you take the two tensors and you go element-wise, and then you multiply them together, and then you add them up. Okay, that's all it does. And of course, you get a scalar out of it. All right. Okay, so well, and I forgot, and I'm gonna put it here again just for completeness, the definition of the gradient of a vector field, which is a tensor field, which is basically derived bi xj ei tensor ej. Okay. Okay, so when we use that identity, what we get essentially in the end, so remember that we're interested in replacing this term right here, right? Which is, if you look at what we have done, is this term right there. Right? So basically it's going to be this guy minus that guy. Yeah, so when we do that, and notice that so far I have kept the fact that the stress tensors, so I have kept the fact that I'm using the transpose of the stress tensor, but you all know that the stress tensor is symmetric, right? That is the result of a balance of angular momentum, and you should have seen this in previous courses, right? But I'm keeping that so far because I don't want to make any assumptions in regards to the structure of the stress tensor, and you will know why in a few minutes. I don't need to make an assumption, basically. Right? I don't need to assume that the stress tensor is symmetric to get to the final formulation. So when you do this, you get, well, the integral on omega of w dotted with this is equal to the divergence of that quantity minus yeah. And of course, I am missing one term, right? So when this is just to express the same thing that we have done here, but I just basically place the integrals. But then when I put back into the whole thing, the only term that I'm missing is basically the term with the body force, all right? Okay. So what I'm going to do right now is I'm just going to move away. So I'm gonna really plug this back into the weak form, and what we're going to do is going to move away the term that has these balanced derivatives to the other side of the equation, the same way we have done it over and over and over, and then we're gonna keep on the left side of the equation the term that resulted from the boundary, right? That we're going to apply the divergence theorem again in exactly the same way we did last class for heat conduction, plus the term that has the body force. Okay, so what do we get? Well, we get that this term is going to be equal to this term plus that term. Okay, now, as I said, we're going to look into this term here. And if you remember the divergence theorem, once again, we took something, an integral that is over the entire volume, right? And we replace that with an integral over the boundary. So this is going to be equal to the integral over the boundary. And then we take basically that quantity that I have here, and I dot it with the normal. And of course, remember that this is basically for all w's in V naught. Okay. Yeah, and again, as last time, as we did in heat conduction, this entire integral over the entire boundary has to be expressed, right, as three different terms, because we have three boundaries. But if you remember, again, we choose function from this space from which I know that the value of those functions is equal to 0. It's a Dirichlet boundary, so this integral right here turns into two integrals. Now, because of a property of the transpose of a tensor, so you may know from previous courses that U dotted with T is a tensor, V is equal to V dotted with the transpose of that tensor operating on U, just by the property of a tensor. So you can see already that this term is going to change, right? And I'm going to write it here. Is going to be equal to the integral of W dotted with sigma operating on N. And look how nicely the natural boundary condition arises without even making an assumption on the structure of the stress tensor, right? Because now I know that this term right here, and I can relate to what we wrote in the beginning of the strong form, these guys can be replaced by these guys. Yeah? So then, I'm going to move this a little bit to the right, to the left, I mean. And then I'm going to write this as an integral of gamma t, and I'm going to say W dotted with the traction plus H, and I'm just going to copy this guy because I'm lazy. And I ran out of space. And that's pretty much it. Remember that we eliminated from the formulation the reactive tractions because we're not interested in those again. So it's exactly the same thing that we did last time. Exactly the same thing. Yeah. Now, if we use a property that the stress tensor is symmetric, you can actually show that this quantity is actually equal to this quantity, where grad S is, you're just taking the symmetric component, and therefore this is 1/2 of grad W plus grad W transpose, and therefore this quantity right here already shows something that we have seen already above, right? What is it? It has the same structure as what? Yes, as the strain, right? So if you remember here, we wrote the strain has that exact same shape. And now we are making use of the fact that the stress tensor is symmetric, which is a result of the balance of angular momentum. And then we're saying, well, this operation can be written as this. And now, is this a real deformation? No, it's not. It's not a real deformation. And so in some places, you're going to see this being called virtual strain. So when you have the formulation in the way some people call it from principle of virtual work, right? The principle of virtual work is an equivalent statement of weak equilibrium. So in that context, people talk about virtual displacements, virtual strains, right? But it's exactly the same formulation. It's just that in that context, I would say that people don't use that for all functions W or for all virtual displacements or for any virtual displacement. I'm not sure because I'm coming from a from a different, more mathematical point of view, but in engineering is mostly, people mostly use this approach, right? The principle of virtual work, which is an equivalent statement again. Okay. So when we do this, then at the end, what we get is find U in that space such that the bilinear form is equal to the linear form for all W's in that same space. And well, let's write what are the bilinear linear forms now that we have all the terms. Well, so if we look, everything that has U and W is going to be part of the linear form, the bilinear form, and therefore this guy here is going to be part of a bilinear form. Sorry, I meant, where is it? Yeah, well, this guy here. And then everything that is not having U is going to be part of the linear form, and then we're talking about these two terms right here. Although one of these two terms actually has an unknown displacement field, so this term is going to show up in the bilinear form, but this one is known, and therefore it's going to be in the linear form, and this term here, together with the body force term, are going to be part of the linear form because they don't have any dependence on U. Okay, so when we do that, we have that the bilinear form is equal to I call it here UH, but that's exactly what I meant. It's actually U because it's still the unknown value of the field there. So let's keep the same notation, not to be confusing. And then the part of the linear form is going to be equal to the term that contains the body force, which is an integral over the volume. And then we have two terms, one coming from Newman boundary conditions, and another one from the Robin boundary condition. Whew. Okay. So far, so good. And then someone asks, so what happens if you have non-homogeneous boundary condition? Essential boundary condition. Do we have to rederive everything again? Oh, so annoying. So what do we do? Who can remember? Hmm? Huh? Yeah, we want to use two functions. And now we're going to get a bit more mathematical here, just as a definition. We're going to call this a linear variety, okay? So what is a linear variety? Well, a linear variety is just a translation of a space by just a known function. And you may see, well, why are you adding a space with a vector value field? Well, I'm using this in a very relaxed manner, so it's not really rigorous, right? But the idea is very simple. You take any function here, right, and you translate it with another function which actually satisfies the essential boundary condition. We call this a linear variety. Why? Well, because I can say that the restriction of that function in gamma u is going to be equal to my prescribed field. Right? So this is what we call a linear variety. The moment we do that, well, now I'm going to take a function that has this form. U is going to be equal to v plus that function that satisfies my prescribed Dirichlet boundary condition. And now I'm going to take this guy, v, from the same space that I define the functions or the weight functions w. Because again, we get into the Bubnov-Galerkin approximation. Okay, so when we do that, again, very simply, the weak form is find V now, because I remember that I already know this guy. This is a known function that satisfies the prescribed boundary condition. So now I have to find the unknown part of U, which is only V, right? So find V such that now my bilinear form is like this. Because remember, now I'm replacing this U, I'm replacing it right here, right? So remember the distributive property of the bilinear operator. This is going to be equal to the linear form minus the bilinear form applied to U tilde. And this has to be valid for all W's in that. And again, I want to emphasize this. We're looking for the unknown component of U. This part we know. And since the unknown component of V, so of U, sorry, that we call V, is in V naught, and this expression here has to be valid for all W's in that V naught, right? Since V is chosen from V naught and W's are from V naught, again we have a nice symmetric problem, right? And we call this Bubnov-Galerkin. Okay, so, well, again, the finite dimensional or the finite element equations, what do we do? Who can tell me? Really quick. I'm not going to go through the derivation of that because it's pointless. But who can tell me what we do? Yeah.
We write an H everywhere.
Yeah, that's it. We write an H everywhere. So we write an H here, we write an H there, we write an H here. Not here because, well, this one we know, it doesn't really matter. We write an H here, we write an H here, and we also write an H above this, just to denote that the space is finite dimensional. And if you remember, we chose H as a symbol because H has a relationship with the dimension of our elements, the size of our elements. So we are so far dealing with the H version of the finite element method. So the P version is for the next lesson, okay? That's it. We're done with deriving weak formulations. And this is the most difficult one to understand. But as you see, it's all the same. You take your differential equation, you come up with the weighted form of that, right? You do integration by parts, or you apply some sort of identity, right? In the process, the natural boundary conditions are going to arise. In higher dimensions, you apply the divergence theorem, and then you have your weak form. And then you take functions and weight functions. So your try solution and your test function are chosen from the same space, finite dimensional space, and then you get into your discrete equations that then you solve Ku equals F for U. Okay. Are there any questions? This is going to take some time to process. Tell me.
How do we know U tilde?
Oh, you just choose U tilde. That is your function. You can choose any function that satisfies the Dirichlet boundary conditions. Of course, normally in a finite element implementation, we basically use the same type of functions that are used to discretize all the finite elements. And because we normally choose shake functions that have this Kronecker delta property, what you do in the end is very simply, in the implementation, having a known value of the field at those locations, since the shake functions are equal to 1 at those nodes and on the boundary, then what we normally do in the implementation, you zero out rows and columns of the stiffness matrix with prescribed Dirichlet value. We assign ones in the diagonal, right? And then you put that, you have to modify the right-hand side. We'll go through this part because it requires a bit of thinking, but there is a very nice way to deal with this problem of non-zero essential boundary conditions in the implementation, and actually the code that you have already does that. Okay. Any other questions? All right, guys, let's take a 5-minute break, and then we are going to see whether we continue or not with FEM, because it may be too much. Who wants to continue with FEM? One person, two. Okay, we'll see.